So much for your, oh, there you go. 1 second. Got it. All right. Yeah, thank you so much for the really kind introduction and for the opportunity to be here today and talking to you all. This is really just an absolute honor, and I really appreciate it. So today I'll be talking to you about how we can discover tunable materials with unprecedented properties via high-throughput quantum chemical calculations. And so let's kick this off. I think just to set the stage, many of us are already familiar, but to just make sure we're all on the same page, I think we can all agree that solid-state materials and materials more broadly are really important for creating a better future in all regards, whether that be related to producing cleaner energy through the design of new catalysts, or having next-generation electronic devices, perhaps membranes for cleaning our air or cleaning our water, and obviously the list goes on and on. And for all these applications and many more, really at the heart of this is the question, how do we discover these new materials to push the boundaries? And of course, we're familiar with the conventional way in which we do this, right? We come up with a hypothesis of a given material that might be promising. We'll try to synthesize it in the lab. We'll try to characterize it, and we'll test its properties and then go back to the drawing board and iterate this process. And of course, in the context of this talk, I'll be discussing how we can use a computational approach that's very complementary to help guide experiments, particularly when their search space is really large or when we just don't really know where to search. And so specifically, I'll be talking about how we can combine quantum chemical calculations, high throughput computational screening techniques, and recent advances in machine learning to create this accelerated materials discovery concept. And again, what I want to emphasize is that it's not about replacing experiments, but rather being a complementary approach where we're trying to guide that hypothesis generation process. And before I talk about some specific kind of results that I'll be sharing with you, I do want to just set the stage a little bit to describe why this is challenging. And so if you do quantum chemical calculations, obviously these calculations have been done for many years now, but what I want to emphasize is that what's simple for one calculation is rarely simple for 1,000 or 10,000. And I think catalysis is a great example of that. And so here's a very nice figure from a paper from Christine Person's group where I'm doing my postdoc right now, where if you wanted to predict, let's say, an absorption energy on a single material, it actually, even that one simple example can be very complex. We might start with a bulk crystal structure that we run some calculations on, maybe to get the lattice constants. And then we'll take that bulk structure and we'll carve maybe a bunch of different surface slabs with different surface facets, right? And we'll do a bunch of calculations on each of those surfaces, which are indicated by these blocks. And then on each one of those surfaces, you might want to add an adsorbate. But maybe there's multiple possible sites to add that adsorbate, which you don't know until the calculations run. And so you add an adsorbate onto each site. And then maybe you want to do multiple adsorbates, right? And maybe for a catalytic mechanism. So you have to do that process multiple times. And then you want to do some post-processing. And you can see even for a single starting bulk material, you can already end up with hundreds of calculations that need to be done. So really why this is not trivial is we have this complex job connectivity where the workflow is really ill-defined until runtime. The number of slabs and the number of sites, this might not be predefined, especially if you do this across many materials. You also want to make sure that if one job fails, the whole thing doesn't fail. You want to be able to effectively monitor many calculations. So if you scale this up to tens of thousands and a job fails, you don't want to have to be figuring out how and why that was going on. You need to be effectively making adjustments on the fly. So that goes into that automated perspective. So if the SEF doesn't converge, how are you going to automate that process? And you need to make sure, obviously, the output data is easily queryable for doing data science. Now, there are many tools for this, and I will just briefly do a pitch here for one that I've been developing and I've used throughout some of these projects I'll be discussing, which is called the Quantum Accelerator, or QUAC for short. It is meant to be a Pythonic workflow tool to make reproducible and modular workflows specifically for quantum chemical calculations. It's very user-friendly with the idea that you can just import predefined recipes and use standard libraries in the community like the atomic simulation environment to basically run these kinds of complex workflows with just a few lines of code for the user, while still making it very easy to modify for experts. And also with the goal of making the data easily accessible for data sharing and fair data. All the calculation outputs from these kinds of workflow tools, whether it be mine or others that are in the community, specifically from the materials project team, have the output that is metadata rich. So instead of just having an energy as an output, all of the data is collated in a big dictionary that you can store in a database if you like, and you can query using, again, modern querying database syntax if that is something that you prefer. And also using one of several different workflow engines and workflow tools, you can even monitor calculations through nice user interfaces, of which there are several supported by this quantum accelerator code, which makes, again, monitoring these calculations very easy to do. So with this workflow infrastructure, what's on the agenda? What are the specific things that I want to talk to you about? Specifically, I'll talk about 3 different areas. First, I'll talk about atomically tunable framework solids, of which I'll be discussing metal organic frameworks for gas separations, although I also worked on the area of catalysis. And then I'll talk a bit about optoelectronic applications. And then finally, switching gears a little bit to focus on surface catalysis on alloys. And as you can see in this figure here, the number of materials I'll be talking about that in screening within each of these little stories is going to increase as the talk goes by. So if you feel like this isn't really high throughput yet, just hold on, we'll get there. The idea for this is that I'm an engineer, so we do testing before we scale up. And so this was kind of earlier on in my studies before I've really fine-tuned everything to get to the kinds of scales that I'm talking about here. So let me start by discussing atomically tunable frameworks for, in particular, gas separations. And the class of materials I'll be discussing is called metal organic frameworks, or MOFs. And these are so-called designer materials, 2 of which you can see on this slide. Metal organic frameworks are these solid-state periodic framework structures composed of discrete molecular building blocks. So we have an inorganic node. In this case, it could be the zinc-based cluster, or this iron-based cluster, or one of many other types of inorganic nodes, stitched together in 3-dimensional space via these organic linkers. And so you can see here's one of those. And again, this material actually has 2 different types of linkers to form these intricate and beautiful crystalline lattices. And some of the benefits of these materials are that they're highly porous and crystalline, and they have very predictable and tunable structures, which is great from a theoretical perspective, because we can have a good idea about what we might want to make or study. And in addition, this tunability, by changing the building blocks, whether it be functionalizing the linker, changing the linker altogether, or changing the node, you can, in principle at least, tailor these materials in terms of their physical and chemical properties for a given application of interest. It's just a question of which building blocks do you pick. And so to date, 20,000 or so MOFs, depending on who you ask, have been synthesized to date, and you can find them in the Cambridge Structural Database for many of them. And virtually unlimited more can be dreamt up, again, by considering different combinations of those constituent building blocks. And so really the question is, how do we efficiently find promising MOFs for a desired application? So as for some select application areas in the literature and that I've been interested in, there's gas separations, heterogeneous catalysis, electronic devices and optoelectronic properties, and really the list goes on and on. If you open up a chemistry journal, you've surely seen an application for a MOF in one of a variety of different fields, some of which are perhaps more fundamental and more on the fundamental chemistry side of things, and some perhaps more applied. And for this discussion right now, I'll be focusing on gas separations. And so I want everyone to just pause and kind of take a deep breath and just breathe in and breathe out. If you do that, take a deep breath. We all are doing air separation. So what we do is we breathe in the air. It has a variety of different components. And in that mixture of gases, there's oxygen, right? And we have hemoglobin in our blood that is able to selectively bind oxygen, but not other gases like nitrogen. And we do that really successfully. But it turns out that's actually somewhat difficult to do outside of the cellular environment. And so what we'd like to be able to do is do this air separation process industrially in a very efficient and sustainable manner. And as for why we might want to do this, if we want to produce purified oxygen, which is useful for medical facilities, useful for chemical manufacturing, useful for the steel industry, we would like to be able to use air and extract out the oxygen. And that is something that we conventionally do via cryogenic distillation. And so in this little cartoon, which is showing that process, we take in air, we filter out some trace components, and we're mostly left with oxygen and nitrogen. And we can take advantage of the slight but notable differences in boiling points between these two gases to liquefy out one component but not the other. And that is how you end up industrially at large scales having high purity oxygen being generated from. And the dream really would be able to not rely on this cryogenic distillation process, which is very energy intensive and fairly costly, and instead rely on an adsorbent material like a sponge type material that can efficiently separate out oxygen from nitrogen at ambient or near ambient conditions. And perhaps we can leverage the difference in reactivities between oxygen and nitrogen to do that. Now, I should mention, if you don't care about the energy or cost savings aspect of this, that's fine. There are other reasons as well why this is an important process to continue to optimize. And the COVID-19 pandemic has unfortunately shown us that, which kind of showed it, as you saw in the news, these oxygen shortages happening because we have these centralized facilities where we're doing this air separation. And when there's huge peaks in demand, having these kinds of centralized facilities away from the medical areas where we need them can be problematic. And so we'd like to also have on-site and cheap oxygen purification via an adsorbent type material as well. And so I'm going to show a little cartoon here of how this process might look before I show you the results. This is a schematic of a representative metal organic framework, the details of which don't matter except for the metals are in orange. And we have a mixture of nitrogen and oxygen on the left-hand side. And if I hit play in this very crude cartoon, what we'll see is nitrogen goes through the pores, and we might have oxygen bound to those metal centers. So it's selectively binding the oxygen. And then nitrogen flows through, you can collect that and do with it what you like. And if the binding strength of oxygen is just right, you can heat up that framework material and pop off the oxygen and collect that separately. And then repeat that cycle over and over again. And so the question is, how can you find a material that does that? We can, of course, as I suggested earlier, use high throughput computational screening methods to identify such materials. And so here are a family of structures that I looked at in this screening study, mainly based on materials that have been studied for redox reactions. And I chose redox reactions because oxygen binding is often an oxidation process. And so I considered about 100 materials, 2 adsorbates, the oxygen and the nitrogen, multiple possible adsorption modes for those gases, and then several plausible electronic spin states for each one of them. And we can see what the results might show. And so in this figure, I'm showing just a small collection of the data just to not overwhelm you. On the x-axis, we have the metal center where the gas species is being bound to, and each one of these points represents a different metal organic framework. On the y-axis, we have the relative binding strength of oxygen to nitrogen, all calculated from DFT. Anything in red is indicative of oxygen being favored, perhaps by 10 kilojoules per mole over nitrogen 20, et cetera. And anything in blue is favoring nitrogen. And you could just see a little cartoon here of what that might look like, although multiple possible adsorption modes are possible. And so if we wanted to find a promising metal organic framework for air separation, what we're looking for is the largest delta, large difference between oxygen and nitrogen. And so naturally, your eye points to this, this framework solid here, which has the formula cobalt hydroxide BBTA, which I'll explain more in just a moment, since I know that's a mouthful. But what you can see here is that this material is predicted to bind oxygen much more strongly than that of nitrogen. Now, interestingly, we can compare that material to this cobalt chloride BBTA framework, which, based on the formula, seems like it should be a fairly similar material, but clearly has very different properties. In this case, this material is not predicted to be particularly selective for oxygen to nitrogen. And so this gives us a good counterpoint to try to understand why that might be. And I should mention that holds regardless of the type of metal as well. So perhaps this is some general design rule that we can try to find out why this occurs and maybe use that for future studies. So let me introduce you to this family of materials, which I'll call M2X2BBTA for short, the M being a divalent metal, and the X being a monovalent anion, and BBTA being this organic. So this is a family of metal organic frameworks called metal triazolate frameworks because that's what the linker is here. It's synthesized by taking a metal salt like cobalt chloride and this linker, and you will get a periodic crystalline honeycomb-like structure that's shown here. The pore diameter is 13 angstroms, although a larger pore variant can be made with a longer linker. And if we take a zoomed in look into the screen here, what we see is that these metal centers, which are shown in orange, are strung together by these linkers, as well as that monovalent bridging anion. Could be chloride, but it could also be fluoride or bromide or hydroxide or a variety of other monovalent anions. And if we zoom in even closer around one of those coordination environments, what we see is that that metal has a square pyramidal coordination geometry such that a gas molecule could potentially bind right over here. Now, I should mention that this material is stable up to 400 degrees Celsius and can withstand exposure to various gases as well, which is very useful. And so with that being said, we have this tunable framework that's potentially interesting, and let's revisit those DFT calculations just to refresh our memory. The computed thermochemistry is shown here. For this cobalt chloride framework, again, this material is not predicted to be particularly selective for oxygen over nitrogen, pretty much the same value for the adsorption enthalpies, give or take. Whereas the hydroxide-containing framework is predicted to bind oxygen much more strongly than that of nitrogen. And so with this, went to my experimental colleagues at Northwestern and Professor Omar Farha's group and asked them to, if they were willing to, synthesize, characterize, and test both of these materials, which I'm very grateful that they did. And that's what I'm going to show you in this figure. Specifically, this figure is going to show you the experimental adsorption isotherms taken at room temperature conditions. On the x-axis, we have the pressure of gas that's been introduced in units of bar. And on the y-axis, what we have is the uptake of that gas in the framework cycle. And so in red, we also have the oxygen isotherm, in blue, the nitrogen isotherm. And this is specifically showing right now the cobalt chloride framework. And so what we would like to see is that a material would be able to have a much larger isotherm, higher uptake for oxygen than that of nitrogen. But for this cobalt chloride framework, as we predicted from theory, the oxygen and nitrogen isotherms are nearly overlaid. It has a similar affinity for both, which was reassuring. And if we switch to the cobalt hydroxide framework, you can see drastically different behavior. The nitrogen adsorption isotherm is pretty much the same as before, which again is similar to the DFT calculated adsorption enthalpies we might have suggested. Whereas the oxygen adsorption isotherm is clearly very different. The overall uptake is clearly much higher, but this sharp rise at low pressures is indicative of chemisorption, where you start having that limit from no gas molecules to introducing some gas molecules and they stick to those metal centers, right? And that's why you have this very sharp rise here that results in overall larger uptake. And so what this suggests to us is that the computed thermochemistry, one, is a really useful metric. Two, that this hydroxide framework material is able to separate out oxygen from nitrogen, and that this computational screening approach is at least useful from a proof of concept standpoint. Now, I should mention before I go on and to take a full disclosure here that this material is perhaps not the best material ever made. And the reason for that is not actually the thermodynamics at all. The thermodynamics are pretty good here. But actually what it turns out to be is the kinetics, which have often been neglected in the literature. And so it turns out that when you have gas molecules binding at a surface site, most of the times it's barrier, and we assume it's barrier. But it turns out in this case, because there's a spin state change, which I'll talk about in just a moment, there's a barrier associated with that spin change and the geometry change in the material as well. And that kinetics is something that is fairly limiting for this material. But nonetheless, let's try to understand a little bit more about the fundamentals about why this difference occurs, which maybe we can take to other framework solids. So I would argue that there's two major factors that make the cobalt hydroxide framework bind oxygen more strongly than the cobalt chloride. One goes back to that kind of cartoon of hemoglobin I mentioned, which is actually in part able to do this separation based on hydrogen bonding interactions. And the cobalt hydroxide framework can do the same. Basically, you have these hydroxyl ligands that will enable hydrogen bonding interactions with oxygen, whereas if these ligands were chloride species, there's no longer hydrogen bonding interactions that could occur. Simple enough. The second, which is a little bit more subtle, but actually I believe perhaps even more important, has to do with charge transfer. And so I'm showing here the ChemDraw cartoons of what the DFT calculated spins and charges suggest, which is when oxygen binds at the cobalt chloride framework, it mostly fizzy-sorbs. You start in the 2+ state for cobalt, you end at the 2+ state, give or take. It's all bookkeeping, right? The cobalt hydroxide framework starts at 2+, but becomes 3+, and you get a superoxo species. But it's not just this oxidation process. Because hydroxyl ligands are more basic than chloride, it's able to, based on Lewis acid base theory, donate more electron density back to that metal center and help stabilize that oxidation state. So just to kind of reiterate that point, hydroxyl is more basic than chloride, and therefore it can shuttle more electron density back to that metal and help stabilize the higher oxidation state and help reduce that energetic penalty. And if we take a look at the electron density difference map upon oxygen binding, anything in yellow is indicative of reduction, anything in blue indicative of oxidation. And you can see here that for the cobalt chloride framework, there's slight reduction on the oxygen, but it's all relative and it's pretty much just fizzy-sorption. Whereas for the cobalt hydroxide framework, you have substantial reduction on the oxygen, substantial oxidation on the metal center, and those periphery ligands are also playing an important charge transfer role as well. So again, as a proof of concept on a moderate scale, I would say these computational screening efforts are fairly successful. We can, of course, take these same principles and apply them to the area of catalysis. I showed you an example of an oxidation reaction for gas separations, but there's no reason why you couldn't extend this to oxidation catalysis as well, which I've also worked on. And I won't talk about that for the sake of time today, but you can certainly check out some of my prior works in this area if that is of interest. Okay, so moving right along, I just talked about how we can use computational methods to identify promising framework solids for gas separations. Now let's try to scale it up even more. I motivated this with the materials discovery vision, and before I only had 100 or so materials we screened. What happens if we want to study 1,000 or tens of thousands of materials? And what can we do with that data once we've started to generate? And so let me just jump right to the chase here, cut straight to the chase here, and highlight a useful database that I developed called the QuantumMOF or QMOF database. This database was constructed we started with crystal structures from the Cambridge Structural Database, which contains experimentally characterized crystal structures for 1 million materials, of which a subset of those are metal organic frameworks. With some help from really excellent computing resources, quite a bit of compute time, although perhaps not as much as I expected, and the high throughput workflow that I developed, constructed this QuantumMOF or QMOF database that contains computed properties for 20,000 metal organic frameworks and what are called coordination polymers, which are these non-porous analogs of metal organic frameworks, like Prussian blue. This database, which is publicly available, anybody can access it on the materials project or a variety of other areas as well, has geometries and energies, bond orders and partial charges, band gaps and density of states, even electron densities if you're willing to download them. They're quite large, but they're there. Magnetic moments and a whole lot more. And for the sake of time, I'll only focus on one of these properties today, and that'll be these band gaps, in part because there's not really been a data set of band gaps for metal organic frameworks in the literature, and there's a lot we would like to learn about them. So to make sure that we're all on the same page, right, the band gap is describing the energy difference between the edge of the valence band, where the valence electrons live, and the edge of the conduction band, where those electrons can be excited to. And that tells you information about the optical and principal electronic properties as well. So most metal organic frameworks, for context, are insulators. So they have a fairly large band, and they're not particularly good at conducting charge. We might want to design a metal organic framework that is semiconductive or conductive, for instance, for many electronic applications, or if we want to actuate some response in the presence of some analyte. And we also, regardless of making that band gap lower, we also want to be able to understand how to tune and tailor that band gap, because having some understanding about how to do that can be really important for having tailor-made optoelectronic properties as well as photocatalytic properties. Now, many of us here are presumably computational scientists by training, and so it goes without saying that if you want high quality results, you'll have to pay a hefty computational price. And so let's take a moment to really understand some of the assumptions that are going on, because I think this is incredibly important. We take a look at so-called Jacob's ladder of density functionals in density functional theory. As you go up this ladder, you get more and more accurate, hopefully, but more and more computationally expensive. I will say that for the QMOF database, we have properties available at several levels of theory, several rungs of this ladder, not just the fairly cheap GGA level, we call it, but also hybrid level functionals as well, which again makes a very useful resource in my opinion. Now let's take a look at an example material, UIO66. This is a zirconium containing framework. And if we take a look at GGA, meta GGA, and hybrid functionals, you can see that for the PBE level of theory, which is a GGA functional, it severely underpredicts the band gap, which is well known in the literature. A meta GGA functional from Don Trular's group called HLE17, which is meant to improve the band gap, does improve it with respect to experiments, but not great. And then you go to the hybrid functional, and it's right within that experimental window, but takes significantly longer than the time it takes to run the GGA calculation. And I should mention before I move on, the large range in the band gap values from experiments here is because this material is known to have defects, and depending on the synthesis conditions, you might have different crystallinities, but suffice to say, you really need high accuracy functionals to get anywhere within that band gap range. I also think it's very useful to take a high-level overview of the results before I discuss anything in more depth. So here, each one of these points in this kind of strip plot here is an individual metal-organic framework. So there's a lot of points here. There's about 20,000 or so in the PBE data set, maybe about 15 or 10,000, I can't quite remember, in these other two data sets. And they're the same materials, but you can see here that the band gap distribution, this is effectively a histogram on its side, this violin plot, are very different depending on the level of. So for PBE, that kind of lower rung in the ladder, you see that there's this interesting bimodal distribution in the band gaps, which is quite odd. You have this one region down here and one region up here. HLE17, which is a meta GGA functional, again, meant to improve band gaps, does increase the median value slightly, which is presumably good, but really only of this second peak here. This first peak, mostly the same. And if we look at this hybrid functional, obviously drastically different behavior. We have this pretty much uniform distribution and very different overall than the GGA level of theory, which is suggesting to me that there's not just an underprediction in PB, but something drastically being predicted wrong in these lower levels of theory that can only be corrected when you have a hybrid functional arch-copy exchange. And the answer for why this occurs is actually quite simple. Well, I don't actually know all of the details as for why, but I can tell you, at least at a qualitative glance, at least why this is separated apart at a high level. And that's the magnetism. So the points that are in this upper distribution are materials that are closed shell or don't have magnetic character. The materials that are open shell or have magnetic character in that lower distribution. And what we see here is that PBE doesn't just underpredict with respect to the hybrid functionals, as we might expect, but basically predicts nearly very similar value for all the open shell framework materials. Whereas that is pretty much the same distribution for closed and open shell in the hybrid functionals. So that suggests to me there's potentially an even more serious error than just underprediction, which is important to know. I think there might be a microphone on. But moving on, yeah, thank you. Moving on, what we'd like to do is ask, can we train a machine learning model to accelerate the prediction of MOF band gaps using the QMOF database? And specifically, what I'd like to address is, can we reduce that computing time down from thousands of hours per MOF to maybe less than a second using this data? So again, machine learning, this is an area that many of us have perhaps worked in. Others may have just read about it, but really at the end of the day, it's about taking a material that's a crystal structure and converting it into a fixed length vector that's suitable for regression or any other type of mathematical analysis. And so we need some representation to go from crystal structure 2 vector, and that needs to be a different representation for a different material. And so, right, we need to have a feature matrix X that encodes each one of these materials that hopefully we can use to predict, like any regression task, predict a Y value, in this case, the band gap. And we'll have a data set that we split into training set and testing set. Obviously, we train on the training set and we use the testing set to evaluate the model performance, and the model, the model's not seen the data before. And the goal, again, is to train a machine learning model to rapidly predict band gap from X, right? Y from X for a new material of interest using data in the QMOF data. And since this is the first database of its kind for quantum chemical calculations in metal organic frameworks, we kind of didn't know where to start. So we threw the kitchen sink at it. So with my undergraduate mentee at the time, Shaylin, who is now a graduate student at Caltech in their materials department, we investigated a wide range of different representations. Starting with a very simple approach, take, for instance, the stoichiometric formula and do statistical functions like the mean of the elemental properties. Simple approach, but at least it's easy to understand. We can then scale up to more complicated approaches, like what we call a sine-Coulomb matrix in the literature, where you're describing some electrostatic interactions between every pairs of atoms scaled by their distances and their z values. And then there's even more complicated geometric arguments you can make about similarity between structures, which I won't talk about for the sake of time, but you can check out the literature or the SI of this paper for a description. So let's start with the very simple approach of what happens if we train a machine learning model based on an 103 element-wise vector, 120-bit vector, that is 113 elemental fractions and 17 statistical properties of the stoichiometric. We'll do that for every material, and we'll train a machine learning model on the training set, evaluate on the testing set, and what I'm showing here are those results in what we call a learning curve. On the x-axis, you have the training set size, which is how much data you fed the model. And on the y-axis, you have the testing set mean absolute error, which you want to be low. And I put a target value here of 0.3 EV for the band gap, because that is roughly the experimental uncertainty you would get from differences in crystallinity. And also, at least at the time the study was done, is the state of the art in predicting band gaps in inorganic solids. So it's a useful reference point. And I should mention that the results I'm showing right here are for the PBE data, but the results for the other levels of theory are quite similar. And what you can see is that the model does learn, but it kind of starts to plateau. Note the semi-log axis here, or the log-log axis rather. And clearly that model is not reaching that target value. So let's revisit the different types of ways we can represent each material and see how they all perform. You can see that in purple, there's this method called CGCNN, or Crystal Graph Convolutional Neural Network, which is quite a mouthful, but clearly performs quite well. And again, at a high level, the way this works is we have a graph representation of the crystal structure, where the edges or the vertices of that graph are the atoms represented by their atomic number and other elemental properties. And the edges in that graph are the bonds and the bond distance. And then just like Facebook or Meta does with these graph convolutional neural networks to predict properties based on social graphs, we can predict properties via convolutions of the crystal graph, these materials. And again, we want to predict some output, which is a band gap. And you can see that model is able to surpass that 0.3 EV threshold in the limits of large data that we have in the QMOF database, which is very promising. Now, I should mention that this model now is fairly relatively old. There are now a variety of other models that do even better. And because this data is all open source, it is a great benchmark for developing tailor-made models for metal organic frameworks, which is the goal of this study. And there's now been probably half dozen, if not more, new machine learning models made from MOFs that were trained on this QMOF database to tailor their architecture, which is great. Now, taking a closer look at that CGCNN performance on the testing set, on the y-axis, we have the machine learning predictions. On the x-axis, we have the DFT results. You want all the data to be on that line of parity. And overall, it's a pretty good result, especially for a first attempt. R squared is about 0.9. The mean absolute error, again, is below that 0.3 EV threshold, and fairly similar results across the range of band gap values. There's some more scatter around the 0 EV band gap, or the metallic region, which is not surprising because there's smaller data in that region. And also it's just more exotic in general for these metal organic frameworks. So with this trained machine learning model, what can we do? Well, we can predict high accuracy band gaps at a variety of levels of theory really quickly, much faster than we can do with DFT alone. And I want to highlight just a couple of interesting examples that are admittedly somewhat arbitrarily selected, but just are meant to make a point. So on the left-hand side is one material that the machine learning model identified as being metallic, which again was quite rare for framework solids. It's the silver-based cluster here, or this framework material here. This has actually been known in the literature to be metallic, so that was very reassuring. This material over here is a perhaps more conventional metal organic framework composed of two metals, iron and gold, and it has a band gap of 1.2 EV, which is quite unusual for a metal organic framework, relatively low. But what's interesting is that if I change kind of the animation here to show you, instead of it being above 15 degrees Celsius to below 15 degrees Celsius, the difference in spin state here changes the electronic structure from being 1.2 to 2 EV. And if I go back and forth, you can see it's not just the band gap change, but also the structure is changing as well. So this is indicative of a spin crossover material. There's been prior magnetic studies done on this material, which is how we know the temperature difference. But from DFT, we can predict the different spin states and their resulting properties. But what this suggests is that this kind of material might be potentially a stimuli responsive material, where you have different optical and or electronic properties as a function of temperature, which is very interesting. I should mention that this is actually an area that is very difficult for machine learning, and most of the machine learning models will fail to predict the difference between these two structures, because if you base it solely on the geometry, they're really similar. And so that's an area for future improvement. How can we design machine learning models that can say, this is the high spin configuration, and this one might be the low spin configuration, because the properties will be very different. I don't actually have an answer to that. So if you want to take a stab at it, the data is available. Speaking of data availability, it's all available on the Materials Project, which is a resource developed at Lawrence Berkeley National Lab and Christine Person's group, where I'm currently working. So check out the MOF Explorer page on the new Materials Project website for more. I'm going to revamp this even further over the next couple months to have even more data. So if there's more data you would like and you don't see it, just hold on or send me an email and we can work on getting that online. So I just told you about developing machine learning models and a first of its kind database for rapidly predicting MOF electronic. And I want to take the last few minutes here to just showcase a different class of material properties and materials altogether that we can use these kind of computational methods to predict and discover some interesting phenomena. Specifically, let me set the stage with describing the difference between homogeneous and heterogeneous catalysis and how single atom alloys can fit into this picture. We're all familiar with homogeneous and heterogeneous catalysts, right? We have homogeneous catalysts that are these molecular systems that are chemically tunable. They have uniform active sites and they're often very selective, but they may be difficult to separate from the chemical products. But of course, we as chemists and even chemical engineers love them for their tunability. Heterogeneous catalysts, which are more often used in industry, have trivial separation because they're solids. They're often quite stable, but they actually are very complex to model and to understand, right? They have very irregular active sites, and even the simplest structures have complex electronic properties to modify and understand. Now, recently, there's been this class of materials called single atom alloys, which actually Charlie Sykes over at Tufts, where I did my undergrad, has pioneered quite heavily and inspired a lot of this work as well, where you have a host metal and a very dilute dopant metal on the surface. In this case, 255 silver to 1 copper ratio, copper being in orange here, which can in principle have many benefits of both. You have clearly a heterogeneous catalyst, solid state structure, but you have chemical tunability by changing the host and the guest, and you have effectively uniform active sites in the limit of the dilute limit. Additionally, there's a paper that was published in Nature Chemistry discussing how there's a very unusual electronic structure property in these materials, where they behave not like solids for these dopant metals, but more like a molecule. And I'll describe what I mean by that in just a moment. But suffice to say that if a material has unusual electronic properties, it can have unusual reactivity. And the question is this phenomenon rare? Why does it occur? And can we leverage this for catalyst design if it's more general? So with this question in the back of my mind, I joined the materials project folks at Lawrence Berkeley National Lab. And I said, what can we look at? Well, there's not just from MOFs, the materials project. It has many inorganic materials and many density of states as well that you can just download. So that's exactly what I did. But before I show you the density of states, I want to make sure that we all understand what I'm talking about. So we know from general chemistry, right, when we think about orbitals of an atom, that we have these discrete energy levels, that they're separated in energy. And when we think about a solid, there's also orbitals, but those energies are squished really close together such that they effectively form a continuity that we call a band. And we have a region that's occupied, a region that's occupied, unoccupied, and right, that band gap was separating those if there is a band gap at all. I'm going to flip this figure on its side for the sake of the rest of the figures I will show, where on the y-axis we have the density of states, which is effectively a histogram describing the energetic distribution of the electrons in your material. And if we were to look at the d orbital projected density of states of an isolated copper atom, we know from our general chemistry perspective that those orbitals have the same energy, and it should be just a really sharp line. But if we include some temperature fluctuations, we might have a very narrow Gaussian, if you will. If you contrast that with the d projected density of states of a bulk copper structure, what we see is a very different picture. We have these delocalized electrons in relatively broad bands, and even the simple copper structure clearly is a very complex electronic structure. If you look at this and say, I don't really know what to make of this, that's understandable because that's the point I'm trying to make. It's a very complicated electronic structure, even for simple material, relatively speaking. So with that in the back of our mind, I went on the materials project, and you could do it yourself, went to this copper silver 3 compound and went to the density of states. And here's what it shows. In gray is the density of states for silver, and orange is the density of states for the copper atoms in this silver copper compound. And you can see that the silver is nothing special, but the copper has this very, very narrow electronic structure, this very narrow density of states on the d orbitals that is reminiscent not of that solid, but more like the atom picture, that lone atom, which is interesting. And again, this was motivated by prior work that looked at the even more dilute case. This is kind of the standard definition of a single atom, where we have this dilute limit. And prior experiments had shown exactly this, that this d orbitals, these d projected density of states on the copper are narrow such they are behaving more like an atom. And so with this being said, we can show that you don't need this highly dilute limit at all. But more importantly, we can potentially use the materials project to discover new materials with this unique and exotic electronic structure property and see maybe what can that do for catalysis. So I went to the materials project, which has 150 or so thousand materials, about 88,000 of which have computed density of states, and filtered them out by several criteria, including a stability criterion as well. And depending on the criteria you use, you end up with about 200 to 300 or so materials with this free atom-like character, which in the literature, there's only a few that have been reported at all. And so if we take an example material like this nickel platinum compound, this would not pass our funnel because there's nothing exotic about these two atoms in nickel and platinum, nickel platinum compound. But if we were to take a look at gold nickel, you can see the nickel shown in orange has that free atom-like character, if you will, that has this localized d state in energy space. And that would pass our funnel. And to show you a couple of examples, I'm obviously not going to show you all 300 and change. You can check out the data set in chemical science if you'd like, but there's a variety of binary and ternary compounds with this behavior. We have a sodium palladium compound with free atom like palladium, a calcium platinum compound with free atom like platinum, a nickel gold compound with free atom like nickel, and even ternary compounds like this gold copper zinc compound with free atom like copper. So a quite diverse range of structures. And to really wrap this up, we can ask, what does this do for reactivity in general, right? It's nice to know that these exotic properties exist, but what can that do for us? And like any chemist or chemical engineer, I went to CO, carbon monoxide, as my first bet because that is a common probe molecule. It is also a very common intermediate in a wide variety of thermo and electrochemical reactions. And also just understanding how to tailor the CO binding strength can be useful because CO is often a poison on the catalyst surface that can prevent further reactivity. And so what we'll do here is take an elemental reference structure like palladium and compare the CO binding strength with binding on a similar palladium site that has free atom-like character and see how does the CO compare. So for this example, CO binds very strongly on palladium-101, but on this calcium palladium gold compound with free atom-like palladium species, the CO binding is much weaker. And we can ask, is that something that is general or just for this material? And it turns out the answer is mostly yes. And so from the DFT calculations, each one of these bars here represents an elemental reference structure like the palladium here. Each point represents a different intermetallic compound with those free atom-like D states that I mentioned from the screening study. And you can see for rhodium, iridium, palladium, and platinum binding sites, that CO is binding weaker in the free atom-like structures than in the elemental reference structure. Now, that's not necessarily true for copper. There are many complex reasons for why that is. Check out the paper for more details. It's really an interplay between hybridization of the orbitals and the orthogonalization energy penalty of those orbitals arranging. And we have an empirical model to describe that in the paper. But at least for these rhodium, iridium, palladium, and platinum species, what we can say is that these free atom-like states often weaken CO adsorption, which could be a useful design rule. Now, going forward, and this is pure speculation, but something I think is very interesting potentially, is that we might be able to take advantage of the fact that the electrons control the catalysis and the fact that these materials are very tunable and have very sharp, narrow electronic states, and potentially tailor the electronic structure of catalysts for activating certain chemical bonds, but not others. Because we know that resonance can help reduce barriers, and resonance is just energetic overlap between the orbitals on the surface and the orbitals of the bonds you wish to activate. And so potentially for a given reaction, we might be able to use this kind of design principle to figure out how could we maybe tailor the electronic structure to activate specific chemical bonds, but not others. So an area for future work. So as a quick recap, I showed you how we can use high throughput computational methods to investigate and identify promising materials for gas separations as it relates to metal organic frameworks. We then scale this up even more to construct the QMOF or QuantumMOF database, which is an open source database for electronic structure and geometric and chemical properties in general of metal organic frameworks and coordination polymers. And then switching gears, I discussed how we can use big data resources like the Materials Project, not just for MOFs, but for finding unusual electronic properties of inorganic solids, in this case, free atom-like electron states. So with that, the future of materials discovery is extremely bright, in my opinion. There's an enormous amount we can do. And with the recent advances in machine learning, there's really no limit. And I'm sure many of you have seen all of the news about ChatGPT and all these generative modeling techniques. And so there's a lot of that we can apply as well, which I'm sure many of you are also thinking about. Many thanks to those who made this possible, especially my PhD thesis advisors, Randy and Justin, my Miller Fellowship host, Christine, the whole Materials Project team who has provided an enormous amount of insight into how to do these kinds of calculations, the many collaborators who made this work possible, the Miller Institute for funding, and of course, thank you all for listening. And I will do the quick obligatory pitch that I will be starting my group next year at Princeton. So if there's specifically anybody interested in doing a PhD, if you know a friend who wants to do a PhD in chemical engineering at Princeton in computational area, please send them my way because I'm really excited to work with a bunch of folks. So with that, I will conclude. So thank you very much again for your attention.
That was awesome. Thank you so much, Andrew. Really appreciate you giving such a thorough and intuitive talk. I think all of our students will really appreciate that because here in the chemistry department, we often think about molecular orbitals before we start thinking about bands. Though at WashU, we do get into it a little bit in Gen Chem, so it's better than maybe other places. Anyways, with that, we now have time for questions. So we have about 6 minutes until the top of the hour, but I'm sure Andrew wouldn't mind staying a few minutes after that if you wanted to stick on. But in the interest of opening this up for people to ask questions, what we usually do is start with any of the students, undergraduate, graduate, who have questions for Andrew. So just raise your hand and I'll and ask your question.
Any level of question is accepted. It could be a really high level question, a philosophical question. So don't hesitate if you have any question at all.
Okay, I'll open the floodgates to potentially other questions from not just undergrads and grads. So does anyone else from the audience have a question for Andrew? Otherwise,
hello.
There we go.
Hello.
Can you hear me?
Yes, I can.
Thank you for the very nice talk. I have a question. Can you explain why are the entry level